Okay, so our goal in this lecture is to discuss some general theorems on the convergence of sequences. And the first such theorem is that the limit of a convergent sequence is unique. This should be intuitively clear, I think, because a sequence converging means that the sequence is getting closer and closer. This is just the intuitive feeling of a convergent sequence, is that the sequence is getting closer and closer to some particular real number. But you can't be getting arbitrarily close to one real number and also at the same time arbitrarily close to a different real number. Okay, so that's the basic feeling, and we'll prove this. We'll prove this rigorously using the definition that we talked about last time. So here's the proof. So let's suppose that we have a sequence and it's converging to some A, and that same sequence is also converging to A prime. Now, there are a couple of different ways to proceed. One way would be by contradiction, to assume that A and A prime are different and then derive a contradiction from that. That would be an interesting exercise for you to try, maybe based on the ideas in the proof that I'm going to give. The proof I'm going to give, the idea is what we're going to do is show that the difference between A and A prime is arbitrarily small, that it's less than epsilon for any positive epsilon. And we showed in a previous lecture, I think maybe it was in the first lecture, that if you have any real number, which is any positive real number, which is less than any arbitrarily given positive number, then that has to be zero. Right, so if you have some real number which is non-negative, but it's also less than any arbitrarily given epsilon, which is greater than zero, then that means that R has to be equal to zero. Okay, so we showed this by contradiction, I think, in the first lecture. I think the idea is intuitive enough. So we will show that that A minus A prime, the absolute value of it, is less than epsilon for any given epsilon greater than zero. And the basic idea here is that if you have, so let's say this is A, and we have A prime, and we also have our sequence of ANs, right? And so the ANs are getting arbitrarily close to A, right? And the ANs are also getting arbitrarily close to A prime. So we can make the distance between the ANs and the A arbitrarily small, but also we can make the distance between the ANs and the A prime arbitrarily small, right? So if A is arbitrarily close to AN and AN is arbitrarily close to A prime, well then A and A prime should be arbitrarily close, right? We can make this distance as small as we want, we can make this distance as small as we want, so the sum of those distances should be as small as we would like, right? So that's the basic idea. And the technical tool that we use is the triangle inequality. So the rough calculation here that you can do for yourself based on this picture is the following. So the distance between A and A prime, that's the thing we really want to measure, right? But we have this AN, this is our middleman. So you think about the triangle, right? This is, we want to go directly from A to A prime, but we can have this stop-off point in the middle, right? This third point. So you're thinking about like a triangle AB, we want to measure directly from A to B, but we can measure that indirectly by going from A to C first and then C to B. That's kind of the rough conceptual scheme. So A minus A prime, this is equal to, it's just a little algebra trick which is very common. We can look at A minus AN and then add back the AN, right? This is just add and subtract the same thing. You don't actually change anything. And now we see we've put AN in the middle here. So now we're going to compare A and AN and A prime. And the triangle inequality, remember, just says that for any two real numbers, say R and S, R plus S in absolute value is less than or equal to R, the absolute values of R and S. So this is going to be less than or equal to A minus AN plus AN minus A prime. And now the point is, because of these convergences here, we're going to be able to make this arbitrarily small by just taking n sufficiently large, right? We'll be able to make this as small as we like. We'll be able to make this as small as we like. And ultimately, what we would like to do at the end here is see that this is less than epsilon, right? The sum of these two things is less than epsilon. And well, we have two things we want to sum to be less than epsilon. So if we make each of them less than epsilon over 2, right? So if we make this less than epsilon over 2 and make this less than epsilon over 2, that will work out. And we can do this, right? Because we're given this epsilon here. We want to make this total less than epsilon. But we can take from that epsilon and consider epsilon over 2. Right? That's just some arbitrarily given positive number. So epsilon over 2 can play the role of epsilon in the convergence of an to a, and epsilon over 2 can play the role of epsilon in the convergence of an to a prime. Okay, so you don't get confused over. Right, just because it's called epsilon over 2 and not epsilon doesn't change its role as just some arbitrary positive number. Right, so just you can just rename this epsilon over 2 to be epsilon prime or something, and then we can make an within epsilon prime of a. Right, just a change of notation. Okay, so this is the scheme of the proof. So let's try to work this out. Maybe I don't think we probably don't need that. We don't need that, but let's keep that stuff down there until we've written our proof. So we're going to show that that's less than epsilon for any given epsilon. And then what we need to do then is just say that we're going to take our ANs far enough out in the sequence to make this quantity less than epsilon over 2 and make this quantity less than epsilon over 2. Okay, so since AN is converging to A, there is, let's say, n1 in the natural numbers such that when n is bigger than or equal to that n1, the distance between an and a is as small as we want, right? So what we want is epsilon over 2. So we're going to use epsilon over 2. We go out far enough so that the distance between n and a is less than that epsilon over 2. So such that when n is greater than or equal to n1, the absolute value of an minus a is less than epsilon over 2. And then just the same sentence basically for the convergence of an to a prime. So similarly, there is n2 in the natural numbers such that n bigger than or equal to n2 implies that the distance between an and a prime is less than epsilon over 2. Okay, and then all we'll have to do is repeat this little computation down here. So I'm going to erase that. Okay, and then so all we need is for n to be bigger than or equal to both of these in order to be able to use both of these inequalities. Okay, so therefore, so if n is bigger than or equal to, let's say, the maximum of both of those n1 and n2, right? We just need n to be bigger than whichever one of these is the biggest, right? And then, right, if n is bigger than n1 and n1 is bigger than or equal to n2, then n is automatically bigger than or equal to n2, right? So we'll be able to use both of these inequalities. Okay, so if n is bigger than or equal to the maximum of those two, then we see that the distance between a and a prime, that's equal to a minus an plus an minus a prime. And that is less than or equal to the absolute value of a minus an plus the absolute value of an minus a prime. And because n is bigger than or equal to n1, we have less than epsilon over 2 for this one, and because n is also bigger than or equal to n2, we have this one is less than epsilon over 2 plus epsilon over 2, which equals epsilon. So indeed, the distance between a and a prime is less than epsilon, and we are finished, which completes the proof. Okay, so that's how we prove that proposition, and this is a fairly standard kind of way of doing things. So this showcases some fairly standard tools like this little algebra trick to kind of, and then utilizing the triangle inequality. Okay, so if you can split your quantity up into multiple quantities which can be made arbitrarily small, then you can make the original quantity arbitrarily small. Okay, by just sort of dividing up the portion of the smallness here. So in this case, we had two different things which could be made arbitrarily small, and each of them shoulders half of the burden of making the original thing arbitrarily small. Okay, this is sort of standard technique for dealing with convergence proofs. Okay, so our second theorem, general theorem about convergence sequences, is that a convergent sequence is bounded. And I have to tell you what this word bounded means. So a sequence is bounded if there is a real number, positive real number, m, such that the absolute value of all of the terms in the sequence are less than m for all n greater than for all natural numbers. So basically, this just means, so here's our real line, here's 0. Then what you can do is, so the m is like some far out distance here. So you can go out that far, m in that direction, and negative m in that direction, and your sequence has to stay inside these bounds for all n. Okay, so the entire sequence is bound up in that interval there. Okay, so that's what it means for the sequence to be bounded. That it just has some bound. It's not allowed to go arbitrarily far out in either direction. Okay, and so notice that the converse of this theorem is definitely not true. So last time, right, we looked at the sequence which is just alternating ones and negative ones. So if we look at 0 here, and we have 1 and negative 1 here, of course we can take our m to be, say, 2. So we have 2 and negative 2. We had this sequence which was just bouncing back and forth between 1, negative 1, 1, negative 1, 1, negative 1. Right, that's clearly bounded, but we saw last time that it is not convergent. So just because a sequence is bounded doesn't mean it's convergent, but our theorem says that a convergent sequence is bounded. And so one corollary of this theorem is that the other divergent sequence, I apologize, I keep saying series instead of sequence, just, I don't know, some weird tick in my brain. So the sequence we looked at last time, an equals n, right? This is clearly not a bounded sequence by the Archimedean property of the real numbers, right? Any real number, any potential m that I try here, there's going to be some natural number bigger than that m. Okay, so this sequence is not bounded, right? So clearly the sequence an equals n is not bounded. And by the contrapositive, that implies that an equals n is not convergent. Okay, so this gives a slick proof that this sequence we looked at last time is not convergent without going through the definition of a divergent sequence. Okay, so you see that convergence implies bounded, so not bounded implies not convergent. Okay. So now we'll look at the proof of this theorem. So let's look at the proof of the theorem. Okay, so suppose that our sequence is converging to some real number a. Okay, so what's the idea here? Why is the convergence here going to imply that our sequence is bounded? Well, it's quite intuitive. Let's say, so here's our A that our sequence is converging to. And so what that means is that the tail end of the series is getting, there we go again, tail end of the sequence is getting incredibly close to A, right? So sort of the majority of the sequence, right? The infinitely many terms at the end of the sequence are in some neighborhood of this A here, right? So for example, if I take, say, epsilon equal to 1, so if I look at A plus 1, A minus 1, then the tail of the sequence is going to fall in here, right? So that means the tail of the sequence is clearly bounded. So let's say, I don't know, if 0 is over here, right, then all I have to do is take my m bigger than a plus 1 here, and that's going to cover cover all of these terms. So that's going to bound all of those terms. What about the rest of the sequence? Well, the rest of the sequence, there's only finitely many of them, right? So we have the whole tail of the sequence covered. So, starting with some a sub n is in there, and then beyond is all in that little interval there, and then the rest of it is just finite, right? So there's there's a1, and there's a2, and a3, and a4, etc., and then you have n plus 1, or sorry, not n plus 1, n minus 1, and then an is in here and the rest of them are in there, right? So all we have to do is cover each of these finitely many points out here, and then just cover this this whole interval, which we know is taken care of. So basically what we have to do is, as long as our m is big enough, as long as our m is bigger than the absolute value of all of these things here, right, of all of these individual a's before the an, right, as long as our m is bigger than that, and as long as our m is bigger than, let's see, wherever a is, we need to go one more in the direction further out, right? And it could be that a is negative. So really we'd want to look at the absolute value of a, how far away a is from the origin, and then maybe plus 1 beyond that. So really our m just needs to be bigger than whatever the absolute value of a is plus 1 to cover this whole thing, and then bigger than the absolute value of all of these individual points here. So that's the whole idea of the proof. And I think it'll make things slightly easier. Actually, this definition here, you can change this less than to a less than or equal. That might be more convenient in practice. So, right, if you can make the ANs less than or equal to some m, then considering m plus 1, right, then they would all be strictly less than m plus 1. So the two definitions are equivalent. Okay, so let's look at the proof here. Supposing we have this convergence, well, what we have is that we can put the majority of this sequence in an epsilon equal 1 neighborhood around A. So there is an n1, I guess I'll just say n. So there's an n such that when n is bigger than or equal to that n, the distance between an and a is less than 1. Okay, so that's what we talked about in that picture there, and so that's going to allow us to control all of the ANs that are bigger than this n. And now we're ready to say what m is. This m just has to control all of the finitely many ANs before this capital N point, and then it just has to control everything in this epsilon equal 1 neighborhood around A. So we can set m equal to the maximum of the absolute value of a1 up through the absolute value of an minus 1. Okay, only finitely many things there. And then we'll also do the absolute value of a, and then plus 1 to cover that whole neighborhood around a, as we discussed in the picture. So then what we have to show is that the absolute value of an is less than or equal to this m for any n. Okay, so if n is equal to 1, 2, etc., up to n minus 1, then an is less than or equal to 1 or less than or equal to m, by definition. Okay, because m is the max of all of these numbers. That means that m is bigger than or equal to all of these first n minus 1 guys here. Okay, so those are covered. And additionally, so on the other hand, if n is bigger than or equal to n, then, well, let's see, we have to somehow bound the absolute value of an. So let's think about this. We have 0 here, and here's our limit point a, and we have a neighborhood around that, and we have one of our an's that is in here, right? And what we want to do is control the absolute value of an. The absolute value of an is just the distance from 0 to an. Okay, so we want to control that distance. And what we're going to do is just use this a as a waypoint. Okay, so instead of directly measuring this distance here, we'll measure the distance here from 0 to a, and then from a to an. Okay, so in other words, we're doing a triangle inequality thing. So again, this is showcasing the same trick as in the previous proof. To get a involved, you just add a and subtract a at the same time. So we subtract and we add. Okay, and so let's, and then if you think about them as two terms like this, you apply the triangle inequality. So this is an minus a plus absolute value of a. Okay, and then that absolute value of an minus a, well, but since n is bigger than or equal to n, that's less than 1. So this is less than 1 plus absolute value of a, and that is less than or equal to m by our definition of m. So this is less than or equal to m, and that completes the proof. So absolute value of an is less than or equal to m for all m, as claimed. Okay, so one of the standard, or some of the standard manipulations you do with sequences and limits of sequences in calculus is to apply some kind of arithmetic to them. So we are going to justify that arithmetic from the definition. We're going to look at the proofs of those things. So if we have two convergent sequences, if you take a convergent sequence and multiply it by some uniform constant, then that converges to that same constant times whatever the limit is. And we also have the limit of the sum of two sequences. So if we form a new sequence by just adding the nth terms, and that's the nth term of your new sequence, the limit of that sum is the sum of the limits. Okay, and the limit of a product is the product of the limits, and the limit of the quotient is the quotient of the limits, provided that the denominator of that limit is not equal to 0. Okay, so as long as this doesn't converge to 0, then this holds. Okay, so these are standard and familiar things from calculus, but we want to look and make sure that we can prove them from our definition. That would reaffirm our sense that our definition is correct. If we can, our definition is a good one if we can prove these things that we know should hold for our limits. So here is our proof. So this is going to be a bit longish. We have multiple parts here. And we have to go back to our definition. So, all right, so make yourself ready. So here we go. So number 1. So we need to show that that C times AN converges to CA. Okay, so we have a claim of convergence. Right? This sequence is converging to this thing. So skeptic says, well, here's your epsilon. I don't believe you can make the difference between this sequence and this alleged limit less than epsilon. So we let epsilon greater than 0 be given. Okay, be given. And what we want to do is we have to show that the difference between our the terms in our sequence and the alleged limit is arbitrarily small. And so we do a little, so this is our scratch work here. So we do a little preliminary computation, see what we can do. What we have control of is the difference between AN and A, right? So this convergence means we can make the difference between AN and A arbitrarily small. And what we have is CAN and CA. So we're trying to control this difference here based on the fact that we can control the difference between AN and A. So we need to make AN minus A appear somewhere. And it's obvious here. So you just pull out the C and you get AN minus A. Of course, this is absolute value of C times absolute value of AN minus A. And ultimately, I want to make this whole thing less than epsilon, right? And what I can do is I can make this thing as small as I want. So given any positive number whatsoever, I can make this smaller than it by just taking n large, right? So in order for this to be less than epsilon, so what I have here is I'm going to be carrying this absolute value of C along, right? I mean, so basically what you can do is, yeah, so let's maybe think about it this way. Sorry, excuse me, 1 second. So you want ultimately for this to be less than epsilon, right? So what you want is for your AN minus A to be less than epsilon over absolute value of C. And of course you can do this, right? You have your C, your epsilon has been issued as your challenge. You also know C, so you can consider the number epsilon over absolute value of C, and you can make AN minus A less than that target because you know you have convergence here. Okay, so all this will work out as long as we can make AN minus A less than this thing. There's only one little wrinkle here, is that we're assuming that C is not equal to 0 to be able to do this division, so we'll just have to make a little note of that. Of course, if C is 0, then we just have a sequence of zeros, and we're claiming that a sequence of zeros converges to 0, and that's basically obvious. So maybe we'll just say that at the outset. So if C equals 0, then the convergence of the sequence 0, 0, 0 to 0 is obvious. Or maybe I won't say obvious. You should really check it from the definition, but it's incredibly straightforward. It's the easiest probably type of convergence proof you could do. So the convergence of that to 0 is easily established. So assume that C is not equal to 0. Okay, and we did our work here, so let me just erase this part that's in the way and just keep that last bit there to remind us what we're going to do with with the fact that we have convergence. So since AN converges to A, there is an n in the natural numbers such that n bigger than or equal, little n bigger than or equal to big N implies that the distance between AN and A is less than epsilon over C, absolute value of C. All right, C could be negative, so got to account for that with the absolute value. Need to include the absolute value, that's important. Okay, so then I can get rid of this. I already have it written down. Everything is just going to follow from this. So if then little n is bigger than or equal to big N, then we'll see that the CANs are within epsilon of CA. It follows that the absolute value of CAN minus CA, you've already done the hard work at this point. You've done this computation. Once you figured out how big your n should be, how small this should be, you're basically done. So it follows that this equals, we know absolute value of C times absolute value AN minus A, and this is less than this by our construction, and that is equal to epsilon. And so we find that this is less than epsilon, and the proof is complete. Okay, so that's really it. That's the whole thing. All right, part 2. So let epsilon greater than 0 be given. Okay, well, what we have to do is we have to look at, we're trying to show that the AN plus BN can be made arbitrarily close to A plus B. So we need to look at the difference between AN plus BN and A plus B. And what do we have to work with? So we're trying to make this small, right? And what do we have to work with? Well, we can make the difference between AN and A small and the difference between BN and B small. So we just do obvious algebra to get AN minus A to appear and BN minus B to appear. So in this case, straightforward, right? Just sort of regroup your terms. This is AN minus A and BN minus B. Okay, and all we need to do is, right, I mean, these are kind of, these are being added together inside the absolute value. What we have control of is each of these things in absolute value by itself, right? So straightforwardly here, what we're going to use is the triangle inequality. So get used to using the triangle inequality. So the sum of these two things is less than or equal to their individual sums of their absolute value. So it's less than or equal to that. And we want to make this less than the given epsilon ultimately. And as I said before in a previous proof, right, we have two parts here. We want this ultimately to be less than this epsilon, but we can make each of these arbitrarily small. They can split the burden of the epsilon between them. So we can take n large enough that this is less than epsilon over 2. We can take n large enough that this is less than epsilon over 2. And then their sum will be equal to epsilon, right? So if we put our less than there, then we'll have that sum of these two is equal to epsilon. Okay, so that's the basic idea here. So we let epsilon greater than 0 be given. Since AN converges to A, there is an N1. Okay, so we have two different things converging. So we're going to have a point in this sequence in which the difference becomes less than epsilon over 2, different point in this sequence at which it becomes less than epsilon over 2, and then we'll just go the further out of the two of them. Okay, so there is an N1 such that n bigger than or equal to N1 implies that AN minus A is less than epsilon over 2. And since BN converges to B, there is N2, and I'm running out of room, so let me get rid of my scratch work here. All right, so now we know the idea. We're trying to just make things less than epsilon over 2. There is an N2 such that n bigger than or equal to N2 implies that Bn minus B is less than epsilon over 2. So if n is bigger than or equal to big N, and big N here will be defined to be the maximum of N1 and N2, then the difference between AN plus BN and A plus B, we're just repeating our computation now. So this is AN minus A plus BN minus B. That's less than or equal to the sum of the absolute values. And that is less than, the first one's less than epsilon over 2, and the second one is less than epsilon over 2, which is equal to epsilon. And so there, we're done. Okay, so you see again, familiar tricks, familiar patterns of thought hopefully arising, triangle inequality being a big one, and just sort of thinking about, you're just trying to think about in terms of, I'm trying to make a particular quantity small, the difference between this, and what I have under my control is two particular quantities, right? So I can make the difference between these two small, I can make the difference between these two small. So how do I put those two, how do I sort of use that, leverage that information into making the difference between those two small, okay? All right, so number 3, this one is a little bit more complicated, or at least it's a little bit less straightforward algebraically than the last one. So let epsilon greater than 0 be given. Okay, so this time we have a product, and what we want to do is, so we have AN, BN, I want to make the distance between AN, BN, and AB be arbitrarily small. All right, so I'm trying to control this thing, and what I have is AN minus A and BN minus B. And it might not be so straightforward to see how to get these two things sort of involved here. Like there's no obvious algebra that you can do. There is something you can do, and it might seem a little bit not intuitive. So let me try to give you an idea of how to think about this. So you can kind of think about this as so think about the ANs converging to A as like you have, so the A is going to be, so here we are. So A is going to be this length here, and let's say B is this length here. So the AB we're thinking about as the representing the area of this rectangle. Okay, and the ANs, that's some sequence which is approaching the length of that one side of the rectangle. So let's say you would have like AN, right? So your AN would be along here. And similarly with the BNs. So the BNs would be going up this way, sort of approaching the other side of that rectangle. Okay, so AN/BN is going to represent the area of a rectangle, which is kind of, a sequence of rectangles, which is kind of approaching the big red rectangle, right? So you have like a sequence of these blue rectangles, which is approaching the red rectangle. And what we have here is the difference between these two areas, right? So so the AN minus AN BN minus AB. So what will we have? Well, it's easier to think about, right? So it's actually easier to think about. Let's think about AB minus AN BN, just because that's the way I've drawn the picture, so it's easier to think about that. So we have this big rectangle minus the smaller rectangle. What that's going to give you is the stuff in the sort of complement here. So we have this part here. Excuse me. Let's see. So we have this long rectangle here, and then we have this rectangle here. Of course, there's more than one way to do this, so I could have... so I had just deleted that. Have the green rectangle there. So there's other ways to do this. So you could have done the green rectangle going up to here and then the yellow rectangle slightly shorter. So it suggests different algebra, but either way would work. so the AB minus ANBN, if we just look at this picture, what it's suggesting is that this is equal to, let's see, the yellow one is A long and B minus BN tall. So this is A long and B minus BN tall. And then the green rectangle is A minus AN on the horizontal side and BN on the vertical side. Right, and let's just check that. I mean, this is just from a picture, which might have been misleading us. So let's just check the algebra that this actually works. A times B, that gives you the AB, minus ANBN, that gives you that. And then the ABN with a minus sign here cancels with the ABN there. Okay, so that is a perfectly valid expression there. And what we have is the negative of it inside this absolute value. So let's just apply a negative sign through here. That'll just reverse these BN and B and the AN and A. So this is going to be just algebraically equal to A times BN minus B, and then plus AN minus A times BN. Okay. And so all we did here essentially is just we added A times BN and subtracted A times BN at the same time. Okay, so if we had done the green rectangle up here and the yellow rectangle cut off a little bit smaller, I think what we would have done there is add A and B and subtracted A and B. So it would just give you a slightly different expression, but one that would also work. So here, now what we see is we have control over this part here, and we have control over this part here. Right? So we're closer to our goal if we apply the triangle inequality here. So this will be less than or equal to absolute value of A times absolute value of Bn minus B plus absolute value of An minus A times absolute value of Bn. Okay, so ultimately here, let me just cordon this off. Okay, so ultimately here what we want to do is make this less than epsilon, right? The sum of these two things less than epsilon. And so what we would like is to make this part here less than epsilon over 2, and we'd like to make this part here less than epsilon over 2. Right, that would be the simplest thing. And then that would follow that the sum was less than epsilon. So I can make the Bn minus B, I can make that as small as I want. And if I want the absolute value of A times Bn minus B less than epsilon over 2, then I need to take n large enough so that Bn minus B is less than epsilon over 2 absolute value of A. Okay, so that's going to be, so that's one thing. Okay, now the other thing is I want the An minus A times absolute value of Bn to be less than epsilon over 2 as well. Right, so that seems to suggest I want to take n large enough so that An minus A is less than epsilon over 2 times absolute value Bn. The problem is that this is not a constant. Right, so this isn't some given positive number because it depends on the n here. And so I can't take. So I need an unambiguously given target goal, right, to make this to make these less than. It can't be a variable quantity. So I need to do something first to handle the fact that this Bn here is varying. And what I can use is the fact that this sequence Bn is convergent and therefore is bounded. Right? So I can handle those Bn's. So I'm going to know that the Bn's are less than or equal to some m. Right? Their absolute value is less than or equal to some m by the boundedness. So this is because the Bn sequence is bounded. And then I will be able to, now that this is a constant, I'll be able to make that less than epsilon over 2 by making sure that the an minus a is less than epsilon over 2m. Okay, so that ends up being, after all that, so a little bit of algebra, and then we run into this kind of annoying problem about the bn's not being constant. So you have to replace that by a suitable constant to be able to proceed. One other annoying little wrinkle is, again, that we're dividing by this a here, the absolute value of a, and if a is equal to 0, that doesn't make any sense. So we need to take a look at the case where a equals 0 kind of separately. And in that case, our limit here is 0, right? And if we look down here, this term vanishes, right? So we just get that an bn, right? So just the absolute value of an bn is what we have to look at, and that is going to be less than this thing here, right? So it would still be, the algebra here is still the same. So if a is equal to 0, this vanishes and this vanishes, right? So what we would do is we would write an bn as an minus a, right? Because if a is 0, that's an minus a is the same as an times bn, and then we would use the fact that we can control this, and we can control the size of the bn's, again, because they're bounded. Okay, so the way we'll write the proof is we'll look at the case where a equals 0 first, and we'll need to use the fact that the bn sequence is bounded. So let's go up here and see if we can do this. I will get rid of the, I know this picture looks cool, but get rid of that. Okay, so since the bn sequence goes to b, there is m greater than 0, such that the bn's are less than or equal to that m. Okay, in the case where a is equal to 0, in the case where a equals 0, let's see, so, or let's say, sorry, so assume that a is equal to 0. And then we'll enact our plan, but all we have to do is account for this term here, right? So what we'll want to do is we're going to have to control the an minus a. We'll pick our n large enough so that an minus a in absolute value is less than epsilon over 2m. Okay, so assume a equals 0, and because an converges to a, there is an n such that n bigger than or equal to that n implies, I guess I need to get rid of this thing now, implies that, what did we say we needed? We need an minus a less than epsilon over 2m, implies that an minus a is less than epsilon over 2m. So if n is bigger than or equal to n, the difference between an bn and ab, well, since a is 0, this is just an bn. That's the same as, again, because a is 0, that's just an minus a times bn. And that is equal to the absolute value of an minus a times absolute value bn. The bn's are all less than m, so this is m times absolute value an minus a. And then the an minus a's are less than epsilon over 2m. And so this is equal to epsilon over 2, and that's less than epsilon. I guess we could have just done epsilon over m here. But whatever, we already wrote it, it's fine. Okay, now I can get rid of this, we'll go to the general case in which a is not equal to 0. Okay, and we'll just leave this stuff down here for reference. So that handles that case. Now assume that a is not equal to 0. Okay, and then what do we want to do? So we already did the boundedness for the b's, right? So that's fine. We need to take n big enough so that the bn's and are close to b by this amount, and the an's are close to a by this amount. Okay, so now assume that a is not equal to 0, since an goes to a. Since an approaches a, there is n1 such that little n bigger than or equal to n1 implies that the distance between the an's and a is less than, again, we want that less than epsilon over 2m. And since the bn's go to b, there is n2, such that when n is bigger than or equal to n2, that implies that the difference between bn and b is less than, in this case, we want epsilon over 2 absolute value of a. Okay, and then finally, we don't need this for reference anymore, and we can just run through the argument. So if n is bigger, little n is bigger than or equal to big N, which is defined to be the maximum of those two n1, n2, we have that the difference between an, bn, and ab, remember, what we have to do is rewrite that the an, bn minus ab inside there with some algebra. And well, I erased it, but I think what it was we added and subtracted. So we added a times bn and then subtracted that same thing. So we're not changing anything. And then this is going to go with this, and this is going to go with this. So that is equal to an bn minus abn plus abn minus ab. All right, and that's less than or equal to, just doing a couple things at once. We have the bn's in absolute value times an minus a in absolute value, and the a in absolute value times bn minus b in absolute value. The bn's are bounded by m. The an minus a, I guess we're doing all this in one step. The bn's are less than or equal to m, but the an minus a's are strictly less than epsilon over 2m. The absolute value of a is just the absolute value of a, and the bn minus b's are less than strictly epsilon over 2 absolute value of a. And so this all just works out to be epsilon over 2 plus epsilon over 2, which is equal to epsilon. So we have the key, this thing, the key less than is here, epsilon. And so that completes the proof. Okay, so that one was definitely a bit more involved, but hopefully I broke it down enough that you can follow the argument. The basic, the key point was this, you really have to figure out how to algebraically use get the an minus a's and bn minus b's involved when it's not obvious how they're involved there. Okay, so it is just a add and subtract the same thing. You just have to figure out what the right thing is. So hopefully that little geometry demonstration helps you see why that's a natural thing to think about. And then again, we just have using the triangle inequality is a key thing here. And the final wrinkle is controlling these bn's. So you have to essentially replace those bn's by an appropriate constant, because you can only handle these if you know what a constant is ahead of time. Right? So you can say this is less than or equal to any given constant, but if you have something that's variable, you got to replace that variable thing by a constant in order to use what you know about the an minus a quantity. All right, so a number of little bit of subtleties, a little bit of sort of obstacles thrown up every now and then throughout this argument, but we find a way to surmount them, and we're ultimately victorious. Okay, so now the final part of the theorem is part 4, and that's about showing that an over bn approaches a over b. Now, the an over bn, this is just the same thing as an times 1 over bn. So if we think about this as a multiplication, then all we have to do, so we know that the an goes to a. If we can show that the 1 over bn goes to 1 over b, then this will follow from 3, right? So if we can show this thing here, then this is going to follow from, then 4 follows from 3. And so that's the basic idea. So instead of showing this general thing about the an over bn, we'll just look at 1 over bn. Okay, that'll be much simpler. So this follows directly from 3 if we can show that 1 over bn, that sequence approaches 1 over b, converges to 1 over b. Okay, so let epsilon be greater than 0. And so we're going to prove this claim. Skeptic gives us our epsilon, and we're off. So we have to show that 1 over bn, we're trying to control the distance between 1 over bn and b, right? And all we know is that bn goes to b, right? So we can control the absolute value of bn minus b, and with that, we're trying to control this absolute value. So standard algebra here would be to combine these two fractions, so just do the obvious algebra. We have b minus bn over bn times b, right? Just algebraically, absolute value there. That's the absolute value of bn minus b over the absolute value of bn times the absolute value of b. Okay, so basically we want to make this less than epsilon, right? So it would seem that, right, so sort of naively what you would do is I have control over this bn minus b, so this inequality here is that this has to be less than epsilon times absolute value bn times absolute value b. But again, this is not a constant quantity, right? This is not a constant, so this is depending on n, and so we have to do something about that. So before we can do anything like this, we essentially need to replace this bn here with a constant, with an appropriate constant. And you might think that we want to do the same thing as before, like say, okay, bn is going to be bounded, right? So this is going to be less than or equal to some m, but that's not going to work here because what we really have here is 1 over bn, right? So we have 1 over the absolute value of bn. I want to say that that's less than something. Here, this is a inequality that says 1 over absolute value bn is bigger than or equal to 1 over m. That inequality is going the wrong way. I want this inequality here, I want this to be turned around, right? So somehow I need to say that, so essentially what I really want to say here is that the bn's are bounded below by some number, right? So I don't know, so call this just L or something. And then that would tell me that this is less than, which is bigger than 0, say, and then that would tell me that this is less than or equal to 1 over L, right? And then I would be in business. So if I could So if I had that, then what we would have here is that this is less than or equal to the bn minus b over L times absolute value of b. And then I could make that less than epsilon as long as I made the bn minus b's less than epsilon times L times absolute value of b. Okay, so the essential point then is to just show that we can put a lower bound, okay, L for lower bound, on the bn's. All right, so if we can do that, so what's the idea for how to do that? So we need to brainstorm an idea. Before we go writing the proof, we need to brainstorm an idea for how to put a lower bound on the bn's. And the idea is that, well, so our b, remember we're assuming here that our b is not 0, right? Because it needs to make sense to divide 1 by b. So our b over here, which is what our bn's are tending to, is not equal to 0, right? So there's some distance between b and 0. And since the bn's are getting close to 0, right, at some point the bn's are going to be, in absolute value, are going to have to be closer to b than the halfway point between b and 0, right? So at some point, if we put, say, and so if we put, say, that there at, so this is going to be b over 2, right? The bn's will have to be closer than this. So, and because we know that our bn's, to sort of fill out this picture, so this would be, I guess, 3b over 2. So at some point, the bn's are going to have to be in here, right? And in particular, their absolute value is going to be bigger than or equal to absolute value of b over 2. And so in this picture here, your bn's in absolute value would be bigger than or equal to the absolute value of b over 2. So essentially just want to take our, so we want to use the fact that the bn's converge to b to make the bn's in this neighborhood here, right? In this neighborhood of size, whatever this size, the absolute value of b over 2 around b. So that is the basic idea for getting the lower bound on the bn's, okay, just to put them in a suitable neighborhood that's going to be away from 0 of the b's. So let's see if we can do that. So let me give myself a little bit of room here to write. So since bn goes to b, there is n1 such that the bn, so the bn minus b, we just reference our picture, we want that to be less than absolute value of b over 2. Okay, such that bn minus b is less than absolute value of b over 2. Such that holds when little n is bigger than or equal to n1. Okay, and then with that, so what we want to do now is show that we have a lower bound on the bn's from that. So then, thus, when n is bigger than or equal to n1, the bn's, we're just going to use a triangle inequality trick. So the bn's are in absolute value. So we're just rewriting bn as bn minus b plus b. And here we need a lower bound, right? So we need a bigger than or equal to here. And this is our first use of the reverse triangle inequality. Okay, so this is bigger than or equal to the difference of the absolute values of these two things. So we have the absolute value of bn minus b minus the absolute value of b, and we might not know which one of these is bigger, so it's the absolute value of that difference. But in fact, bn minus b in absolute value is less than absolute value of b over 2, right? So this is clearly the smaller one. So this is in fact the absolute value of b minus absolute value of bn minus b. And since this is less than absolute value of b over 2 when you subtract, that's going to be greater than the, right? So you replace that with absolute value of b over 2, and that's absolute value of b over 2. Okay, so that tells us that our bn's do indeed have a lower bound when we're far enough out in the sequence. And so since our bn's have that lower bound, the 1 over bn's, sort of going back to our scratch computation, have the upper bound of that inverse of that. So this is going to be, so we're going to have bn minus b over the 1 over bn's, we're going to have a 2 here, and then a absolute value of b squared, and we want that to be less than epsilon. So what we're going to have to do is take bn minus b less than epsilon over 2 times absolute value of b squared. Okay, so this is our additional thing. We're going to have to consider the point in the sequence in which this becomes less than that quantity there. Okay, again, since bn goes to b, there is an n2 such that the absolute value of bn minus b is less than epsilon over 2 times absolute value of b squared. Okay, and now I can erase all of this stuff. Down here we finally have the information that we need. Such that when n is bigger than or equal to n2. So if n is bigger than or equal to the n, which is the max of the n1 and n2, we find that the difference between 1 over bn and 1 over b is the absolute value of bn minus b over the absolute value of bn times the absolute value of b. The 1 over bn's, that is less than or equal to, actually strictly less than, according to what we did, is strictly less than 2 over absolute value of b times absolute value bn minus b over absolute value of b. And then we can replace this with that. So this is, again, this is strictly less than, we have 2 over absolute value b squared, but then epsilon over 2 times absolute value of b squared, and the cancellations there just give you epsilon. So we indeed have made this difference arbitrarily small, and so the proof is complete. Whew. Okay, so the last theorem told us how limits interact with the operations in the real numbers of addition and multiplication, essentially. And this theorem here is going to tell us how the limit interacts with the order, that it acts nicely with respect to the order. So if we have convergent sequences like this, if you have a convergent sequence and the sequence is less than or equal to some constant, at least far out in the sequence, right? So it really only, I mean, if you only have finitely many exceptions, and then after that, your sequence is less than or equal to some constant, then the limit itself has to be less than or equal to some to that constant. And I think this is pretty intuitive if you think about it. Okay, and then you have the same thing with the reverse inequality here. And then you also have a similar thing when you have two different sequences. So if after some point you have the ANs are always less than or equal to the BNs, then the limit, you have the A's less than or equal to B's. Okay, so you can sort of take limits of these inequalities and preserve the inequalities. Okay, so you have AN less than or equal to BN on the tail end, you can take a limit and the limits preserve that inequality. Okay, so here's our proof. Okay. So we'll suppose here for the sake of contradiction, so suppose for the sake of contradiction, that A is actually bigger than C. And of course, this is kind of crazy. So the limit A is here, right? If we're assuming that A is bigger than C, so C is here, right? The ANs, since they converge to A, are supposed to be getting arbitrarily close to A, but all of the ANs at the tail end of the sequence are also less than or equal to C. Right? So you have this situation where the tail end of the sequence is down here, but is also supposed to be arbitrarily close to A, and that just doesn't make any sense. So clearly in this picture, the ANs at the tail end, they're not getting in this neighborhood around A, right? And so this C here, C is equal to A minus C, right? So this epsilon here is A minus C. That's extending out from A, right? And that makes sense. A minus C is bigger than 0 given our assumption here. So if we so we're essentially going to take our epsilon equal to A minus C and see that we get a contradiction out of that. So let's see. So since AN approaches A, converges to A, there is an n such that little n bigger than or equal to n implies that the distance between AN and A is less than A minus C, right? That A minus C is some positive number. You see, the problem with this is that that's going to mean the ANs have to be in here somewhere. In other words, the ANs are going to have to be bigger than C. So somehow we should be able to see that the ANs are bigger than C by playing around with the inequalities that we have. So what we can do is this AN minus A, we know that the ANs, right, the ANs are less than or equal to C, and C is less than A, right? So, but the absolute value of AN minus A, that actually equals just A minus AN, right? Because the A is bigger than the ANs, since we have that the ANs are less than or equal to C, and that's less than A, right? So what we have is that A minus AN is less than A minus C. Equivalently, AN is bigger than C, right? But AN bigger than C contradicts AN less than or equal to C. This contradicts AN being less than or equal to C. I'm sorry, I just realized something. So when we're using this AN less than or equal to C, that only holds when n is sufficiently large, right? When n is bigger than or equal to that big N. So what we need to say here is, but this thing equals that when little n is bigger than or equal to the given n. And really, I guess, shoot, I kind of messed this up. So this n here, this would be n1, which is different from this n up here. So when little n is bigger than this n here, we're allowed to use this inequality, and then we're allowed to use this inequality when little n is bigger than n1. So what we have is, so this thing here, A minus AN is less than A minus C when n is bigger than or equal to the max of n and n1. Okay, so sorry I was insufficiently attentive to detail there. So you just have to be precise about where your n's, little n's, are coming from. Okay, but that's a simple fix. Sorry. And then that will complete the proof. So number 2 here is going to follow directly from number 1. So if an is bigger than or equal to c when n is bigger than or equal to n, then let's see, then negative an, the sequence negative an, is less than or equal to the constant negative c when n is bigger than or equal to n. So by 1, we must have negative a less than or equal to negative c. Right, because the limit of because we know from the previous theorem, the algebraic limit theorem we just did, that when you multiply this sequence by a uniform constant, it just multiplies the limit by a uniform constant. Right, so by 1 we have that, which is just equivalent to, or equivalently, a bigger than or equal to c. Okay, so that's just straightforward. And then 3 is actually not really any more difficult. We can just reduce this to the case of 1. So by assumption, an minus bn, that sequence is less than or equal to 0 when n is bigger than or equal to n. So thus, a minus b is less than or equal to 0 by 1, and the fact that, so just to be kind of pedantic about this, so limit of an minus bn, right, from the algebraic limit theorem we did, this is the limit of an plus the limit of negative bn, but then I can pull out that minus sign. And it says the limit of an minus the limit of bn, and that is equal to a minus b. Okay, and so that completes the third part. So we just rearranging this, and we just consider the single sequence, which is then bounded above by 0. Okay, so really 3 is kind of just a special case of 1, given the things we already discussed. All right, that pretty much perfectly brings us to the end of time. So I think that's going to be it for the lectures for this week.